lesson 4 is more limits. All about limits, okay? So this time we're going to talk about algebraic manipulation. So some of that you've already seen a little bit, just ways to make it work. If you only observe the graph of a function, it can be misleading when finding the limit of a function. This lesson will explore how to find limits using algebraic techniques and limit theorems. So we're going to talk about all these different methods. Well, most of these different methods. Direct substitution. So can you just plug the number in and usually it works? It does sometimes, okay? Some of our basic limit theorems. Factor cancelization. So the idea of factoring and canceling. Which, did we look at that last week at all or no? See, this is where I'm struggling with what do you know in limits and what do you not know in limits? And I'm not sure. So, but how you can factor and cancel. And then sometimes when you have a 0 over 0, then it will work once you cancel a factor out. Conjugate method, we're going to learn that today. We're going to have to rationalize to get rid of some crazy square roots. We're going to talk about a couple of special trig limits that are ones that are just good to be familiar with. And then L'Hopital's rule is another way to do limits, but we aren't going to do that until we learn how to do derivatives. So thus the reason it will be in Unit 3. Okay? So, substitution theorem. If f is a polynomial function or a rational function, then the limit as x approaches c of f of x is equal to f of c. Provided that if f is a rational function, the value of the denominator does not equal 0. So the idea, if f is a polynomial function, so just a traditional, I want to use the word continuous. I know we don't have a definition of continuous, but a function that just flows, has no breaks and stuff. If it's a polynomial function or a rational function, the limit is equal to when we plug the value in, which is what we've already been working with a little bit. So note, always try direct substitution first. If you get 0 over 0 or infinity over infinity, the goal will be to simplify using algebraic techniques and then try again. Okay? And that's where eventually we'll learn L'Hopital's when the algebraic methods fail us. We have another way. So, and yes, I'm pronouncing it L'Hopital because it's named after a person and it's pronounced L'Hopital, not La Hospital. Just saying. So, sometimes you'll see L'Hopital spelled without the S, just H-O-P-I-T-A-L, and sometimes you see the little accent hat symbol over the O. You know, there's a couple different ways you see it, but okay. Find each of the following limits analytically using direct substitution. So, first thing we're going to try is we're just, 3x squared minus 5x plus 4. Well, if we graph that, that would be a basic parabola, right? It's a basic parabola. So wherever we're at when x is approaching 2, we're going to be approaching some y value. So we can just plug it in to see what value we're approaching. So if I plug 2 in here, 3 times 2 squared minus 5 times 2 plus 4. What, 12 minus 10 plus 4? Doing your math correctly, did you get 6? Okay, so that's basic, just plugging it in. As long as it works, give that a try. Now, occasionally we'll have to backtrack. It won't work. B. Okay, well, plug it in. 2 to the third plus 1 over 2 plus 1. What do we have on top? 9 divided by 3, which is 3. Okay. What about C? Like this one? Do we still have to know a little bit about logs? Yeah. I'm not going to say we do a ton with them, but you still got to know something about logs. So, what's E? Is it a number? Yeah, E is a number, right? Remember, it's called the natural number. It's irrational, just like pi. It's 2.718 something. So plug it in. Natural log of E divided by 3 times E. Okay, natural log of E. This is one you just need to get stuck back in your head. It's one that I taught last year, but here's what I know. What base is natural log? E. So when the base and the inside are the same, what's it equal? The power. What's my power in this case?
1.
1, because there is no power, so it's just 1. 3 times E is 3E. So I'm going to leave that as 1 over 3E. So, work to remember those log pieces. Know the basics, because that's very much a non-calculator problem there, isn't it? So you don't have the calculator to I need to confirm. I'm guilty. I will say I am very guilty of that. Which one is this? I want to confirm. You have to get to the point where you don't need to confirm. Okay, what about D?
2.
What'd you say? 2? I think I could go with that. Cube root of 4 plus 4 is going to be cube root of 8. And cube root of 8 is going to be 2. Ooh, now we got to get our trig brains out. So E, notice they're using theta instead of x. It's just another variable. So the limit as theta approaches pi over 6 is sine of 2 pi, or 2 theta. So this is going to be the sine of 2 times pi over 6. What is 2 times pi over 6?
3.
Okay. My brain goes to 2 pi over 6, and then my brain says, oh, but that reduces, and it's a sine of pi over 3. This is one we have to be able to do this without a calculator. This is one that's on that chart. My brain says memorize. And I'll tell you what, I know my brain works differently, but my brain goes to, okay, that chart I memorized was sine and cosine, and it was, whoops, what am I doing here? Oh, I put the, dang it, pi over 6, pi over 4, pi over 3, reversed by pieces. It was sine and cosine, right? My brain knows 1/2 is right there, and then 1/2 is right there. If I know 1/2 is right there, I know my other piece is square root of 3 over 2. So that's what I need right there. However, do the triangles work too? I don't know how you're memorizing this. Some people teach there's a hand technique. I can't say I've ever taught it, so I can't say I'm familiar with it, but if you Google trig hand technique or something like that, I'm sure you could watch a video on it and get helpful hints that way. Okay, did you do F? Log base 3 of 5 plus 4. Log base 3 of 9. Keep going. What do we know about 9?
I don't know.
3 squared.
9 is 3 squared. And so if I have log base 3 of 3 squared, what is that equal to? 2. Man, mean old teacher. Remember saying you have to remember this stuff, right? Okay. I really should have written these in ahead of time. What is the process for finding discontinuities of a rational function from pre-calculus? So basically think about how did we find, when we talk about discontinuities, how did we find our holes and asymptotes? How did we find our holes and vertical asymptotes? The first thing we had to do was to factor. We had to factor the numerator and denominator. You can write them out, I'm abbreviating. And then after we factored, we had to, probably want to say cancel and simplify. And just simplify. Okay. So that was always step one, is you had to factor that numerator denominator. You had to simplify it if you could. Now, in this curriculum, they tend to call it a point discontinuity. What do I mean by a point discontinuity?
Removable.
Okay, that's the removable discontinuity. It's also known as a hole. Okay, and that occurs, when does that happen? Yeah, a point discontinuity. And again, feel free to make yourselves that is notes that is a hole or it is removable. Because honestly, the vocabulary just needs to be interchangeable. Okay? So point discontinuity occurs when factors cancel, right? I'm kind of trying to shorthand here. And how do you find where that discontinuity is then? You set whatever it is equal to 0, right? And then, so that was a point discontinuity, which is basically a hole. The other piece we have is a asymptote, which vertical asymptotes we also call non-removable discontinuities. What did she call those? I don't have it written down here. Did she call those infinite? I want to say infinite maybe, but she tends to go more with non-removable. So when does a non-removable discontinuity happens? Non-removable discontinuity occurs if, denominator equals 0. The denominator doesn't cancel. Okay, so occurs when, I'm going to say, denominator does not cancel. And then it's the x minus a equals 0 again. There she mentions it, right? That's in the very next thing. You can perform the same algebraic analysis to find the limit of the removable or point discontinuities and the non-removable or infinite discontinuities using what we call the factoring method or cancellation technique. And here's the deal, guys. Officially, we said we should always just start by subbing in, yes? What happens if we sub in here? Just a little side note. If I just go ahead and take the 2, and I just sub in 0 on top, 0 on bottom, yes? Does that mean I get to stop here? No. Okay. 0 over 0, infinity over infinity are what we call indeterminate forms, and you need to try another technique. Okay? We don't know what's happening. Maybe it doesn't exist, but there's also a good chance it does exist. And so I'm going to comment that this is a indeterminate form. Like try again, except not with the same technique. Try another technique. So, other technique we are talking about here is to factor. So, if we work on factoring, will that change things here? Limit as x approaches 2, x squared plus x minus 6. How does that factor? X plus 3, x minus 2. I'm assuming we all remember factoring at this point. X squared minus 6x plus 8. X minus 4, x minus 2, what happens? X minus 2's cancel, right? So now I'm doing the limit as x approaches 2 of x plus 3 over x minus 4. What happens if I try direct substitution now? What if I put in 2? Now notice, when I go to direct substitution, I'm dropping off the word limit. You'll notice every step of the way, I know it's going to annoy some of you, but I rewrite limit every step of the way. Because until I plug those values in, this is still a limit. Okay, so now I'm going to plug in 2 plus 3 over 2 minus 4. Oh, does this work this time? Negative 5 halves. Okay, so yeah, make sure, I'm even going to put a note here, although I don't have much room because I don't have the room you guys do. You guys have plenty of room for all this stuff, right? Somewhat? I have plenty of room in my notes. My notes are all nice and neat. This is horrible. Okay, so I'm going to say quit writing limit. So notice the difference here. After subbing in, okay? So after you sub in those numbers, that's when you quit writing limit. And that's good technique, form to understand there. Okay, graphically looking at the function, we see that just because it is undefined as specific x value doesn't mean we can't find the limit. What we were just talking about during homework check time, right? So she's referring to the Hoover Dam construction example that she had in the notes the other day. Use the graph to determine the value of each limit below. So officially, there's a graph, so I don't go to sub in. But if we subbed in 2 there, I think we get 0 over 0. So that's where we'd have to try factoring and canceling. In this case, though, we have a graph. So as we look at this graph, as x approaches 2, what are you seeing? As x approaches 2, there's a hole. So what's that say about the limit? Can the limit still exist there? Yeah, it's approaching that hole. It doesn't matter that it's a hole, it's approaching that hole. So what is this limit? Ballparking it as, that's what I would say. They're going to give you something like that and not label it precisely. We're going to say negative 2.5, which could also be expressed as negative 5 halves is how I actually wrote it in my note at the times. Know your equivalencies, right? What about as we approach 4 from the right? Where's my graph going? Positive infinity. Well, if we approach 4 from the left, we're down to negative infinity. Based on these two right here, what if I asked you about just the limit as x approached 4? What would you say about the limit as x approaches 4? Does not exist. Because one side's going up, the other side's going down, right? So when they're going 2 different directions, it does not exist. Okay. Oh, I just realized. They gave us negative 5 halves here, didn't they? Okay. I'm oblivious. I didn't see this when I was doing the notes. I didn't see it just now. And well, until just now. Okay. Algebraically finding limits of functions at undefined values. Consider what happens when you try to evaluate this limit using direct substitution. Again, you're going to get these indeterminate forms, 0 over 0 or infinity over infinity if you tried to find these by plugging numbers in, which is why we have to have other techniques. Graphing is one of our other techniques. Factoring would be one of our other techniques. Okay? And it mentions that at the top of the next page. When you get an indeterminate form, 0 over 0, infinity over infinity, your goal is to algebraically manipulate to remove the points of discontinuity. So if it's a whole, for instance, then try direct substitution again. Now, where are we at? Well, we can at least talk a little bit here. Recall in our example, there's a vertical asymptote at x equals 4. How can we determine the behavior of a function at this value of x? And this is more looking at it, okay, if you don't have the graph. Because if you don't have the graph, do you know what that graph looks like? No, that's not a graph that we can just say, oh, yep, I can sketch that graph, piece of cake. No. I mean, we can learn some pieces for sketching that graph, but I can't just sketch that easily. So there, as x approaches 4 from the right, notice it says to pick a value to the right of 4 and then analyze the simplified function. Now, the closer you go to 4, the more accurate, yes? What's a really close number to 4? Closer.
Like, hold it? Okay.
I want closer than 5. Maddie held up 5 for me.
I thought we were doing one numbers.
3.99.
Okay, we're going from the right though, so I don't want 3.999. I want,
4.00.
yeah. Now, she actually used 4.1. I think I like it a little bit better if you try like 4.0001. And so what we can do here is we can plug in the value. Now, I don't have it in my notes. Did we didn't simplify this on the previous page, did we? What does this can't simplify to be? What, x, if we factor? Because I just realized I don't have it written down in my notes. So x plus 3, x minus 2. We did do this somewhere, didn't we? Okay. X plus 3 over x minus 4. So plugging in isn't going to work the other way. But can we plug into that? As soon as I started doing that, I'm like, oh, we definitely did that on the other page. Just not where I thought. So if we plug that in, and we'll have to pick up tomorrow, but doing some number plus 3 over some number minus 4. If we're trying to go from the right, and we're trying to pick a a close number from the right, how about 4.0001? And then we'll have to pick up there tomorrow because the bell's getting ready to ring on me, isn't it? But plug that into your calculator and see what kind of response you get there. And then we'll also do the same type thing on the left. And I'm sure my BenQ will erase overnight, but I don't have a lot on this page, so. Okay. Homework, you can start looking at a little bit of it. But homework will obviously not be due tomorrow. We're going to have to come in and push, I think, to get through all the notes tomorrow. Because there's a decent amount left if you've looked.